Okay, so on a random number generator, I got these numbers, and I'm going to use this to make a binary search tree. So binary search tree obviously is, it's ordered. But yeah, so I'm going to take 19, it's going to be our root, and then I'm just going to add 13. 13 is less than 19, so it's going to be a left child. Then we have 25. So 25 is greater than 19, our root, so it's going to become its right child. Now we're at 17, so 17 is less than 19, but it's greater than 13, so we're going to put 17 here. And now we're at 27, so 27 is greater than 19, and it's also greater than 25, so we're going to put 27 here. And now we're at 11. So 11 is less than 19, and it's also less than 13, so we put 11 here. And now we're at 14, so 14 is less than 19, and it's greater than 13, so now we're at 17, but it's less than 17, so we put 14 here. Now let's go ahead and check if any of these, if this actually qualifies as an AVL tree. So AVL tree, of course, is the height of any of these has to, it has to be equal or differing by 1. So let's say this had a height of 1, this had a height of 2, that's okay. But if this had a height of 1 and this had a height of 3, that's not okay. So I don't know why that's here. Okay, so let's go ahead and look. So this one has 2 descendants, so it has a height of 3. Just it starts off with a height of 1, and for each level its descendants go down, it adds 1 to it. So it started off at 1. Here's a level of descendants, so it goes up by 1. And here's another level of descendants, so it goes up by 1, equals 3. So this one has a height of 3. Now 25 has a height of, 1, 2. So, this is 2, so this is okay, because they only differ by 1. And looking at this has a height of 1, and this has a height of 1, 2. So that's fine. Height of 1 here, but no siblings on the same level. So this is an AVL tree, and let's say we now wanted to insert another number into it. Let's say I wanted to insert, looking at this, a random number 17. So 17 is less than, 17's already in here. Let's say I wanted to insert 21. So 21 is greater than 19, and it's also less than, so 21 here. Now, this hasn't changed anything. In order to get this to violate the AVL principle, to show you the restructuring process, let's see. So again, this one had a height of 3, it's had a height of 2, it's had a height of 2, and a height of 1. So I could violate it by just adding 1 more to this. So let's find a number that will either go here or here. So I guess let's just say we insert 15 into here. Okay, so now inserting 15 into here, this has a height of 2 still. But this now has a height of 1, 2, 3, 4. So this is not an AVL tree because, 4 is, greater than 2 by just, 1. It's not 1 off. So what we have to do now is restructuring. So here, potentially, there can be a subtree here, there can be a subtree here, and there can also be a subtree here. So we're going to go ahead and label these nodes here, X, Y, and Z. And what we're going to do that is just going to go top to bottom. So this is X, this is Y, and this is Z. And what we want to do is we want to map X, Y, and Z to A, B, and C. And we do that but with a in-order traversal. So let me just go ahead and make my little grid here for A, B, and C and see how that lines up. So doing in-order traversal of the entire thing would give us, we go here, and there's a left child, so we go here, and there's a left child, and this is the leftmost element, so 11, and then we would go to the parent, so 13, and to the right, but the right has a left subchild, so we would go down 14, and then we would check for its left, but there is no left, so we would just visit this one, and now we're going to visit the right, and now we'll go back up to where we originally were, and 17, we visit 17, but 17 has no right child, so we're actually just going to go ahead and go back up again to where we started from, which is 19. And so now we've explored the entire left subtree of 19, so we can go ahead and start exploring the right subtree, which is going to be pretty easy since there's only right elements. So we're going to go straight to 25 because, again, we've already looked at the left, already visited the parent. So 25 has no left child, so we don't have to do anything there. And we visit the parent, which is, again, just 25. And now that we're done with that, we would go to the right subchild, so 27, and that's it. And again, the way I was doing that is in order traversal is left, self, or, parent, and then right. So this is our traversal, and as you can see, 15 maps to X, 14 maps to Y, and 17 maps to Z. So looking at how these occur in this order, obviously it's going to be 15, 14, 15, 17. So we have Y, X, Z, which, then maps A, B, C. So let me just go ahead and put this here. So A maps to Y, X maps to B, and C maps to Z. And what we do with this is we get a structure like this, where B is the parent of A and C. And obviously this is in order traversal, so, it's A is less than B is less than C. So A would have to be the left subchild of B, and C would be the right child of B. And of course, since, Y maps to A, B maps to X, and Z maps to C, this is the same thing as X, Y, Z. They're the same. And so we want to go ahead and change the structure to map shot. So I guess I just have to copy this. How would I copy this? Let's go ahead and redraw it. It's 19, 13, 25. And this is 27. 11, 17, 14, 15. Okay, so this is our tree with X equals B, Y equals A, and Z equals C. So we want something more like this. Or this over here, the 17 should actually be 15. And we want Y to be its subchild. So we then have we have Z, which is 17. Okay, so we have something that's not a good set. It looks like pi. Okay, so now we have this going on here. But again, we had these potential subtrees. So let's just say that this is T0, T1, T2, T3. So looking at T0, we can observe that it is the left child of 14, which is y, meaning that T0 is less than y. So it's pretty easy to figure out where T0 is going to go. T0 is going to go here because it's less than y, and y is the least of all these based on our mapping. So it has to be the left subchild of y. Now let's look at T1. So we have T1 here with T1 is the left child of x, so it's less than x, but we can see here that x is the right child of y, which means that while T1 is less than x, x is greater than y. So this must mean that T1 is greater than y. And if T1 is greater than y, then what happens? Well, T1 is the right child of y. So, likewise, we write that here. T1 is the right child of y. Cool, so we have two more trees to deal with now, the subtrees. So let's look at what's going on with T2. So T2 is greater than x. But again, x is greater than y. So, this means actually that, well, actually, no, this is just straight up. T2 is the right child of x. Oh, wait. Okay. So, T2 is the right child of x, meaning that T2 is greater than x. However, x is less than z. So it also follows then that T2 is less than z. So here we have z. There's no available spots to put children for x because y and z are the children of x. So since using our logic, the T2 is less than z, well, this means that T2 is the left child of z. Now, obviously, this just means that T3 is the right child of z. But again, let's go ahead and go through the the math and the reason for it. Just so let's go ahead and look at where T3 is. So T3 is here, and we have this x is greater than y is less than x, and x is less than z. And as we can see here, since T3 is the right child of z, that also means that T3 is greater than z, and actually it's the greatest of all these here. So that means that T3 has to be the right child of z over here, and it is. So yes, and now looking at this, we should actually have an AVL structure. So again, let's do some heights. So here, 1, 2, 3. Has a height of 3, has a height of 2, and this is only a difference of 1, so that's okay. So this is a cleared level. This has a height of 1, and this has a height of 1, 2, so that's a difference of 1. It has a height of 1, so these are all okay. And yeah, I mean, these are all also just, this would all be height 2. So we have an AVL tree. The height principle is maintained even after we did an insertion. So, yep,